Okay, so what if I told you that you could make metal way, way stronger, not by changing what it's made of, but by changing how you cook it? Well, that's exactly what we're going to dive into today, looking at how a totally new cooking method is forging the future of metal.
So let's start with the big question. How do you take a regular metal and just completely level up its strength, its hardness, and its durability? You know, it's this huge challenge that scientists have been banging their heads against for centuries.
And the answer, at least according to this really fascinating new research, boils down to two things. First, you give it a better recipe, and then you find a much better way to cook it. So let's head into the lab, or the kitchen, so to speak, and see exactly how they pulled this off.
Now, every great recipe starts with one core ingredient, right? And in this story, our search for lighter, more efficient materials brings us to this one particular metal that's, well, it's both incredibly promising and seriously problematic.
Meet magnesium. On the one hand, it's an absolute dream. It's so lightweight, which is amazing for making cars and airplanes way more fuel efficient. But here's the catch, the big con. It's naturally a lot softer and weaker than heavy hitters like steel or aluminum. And that trade-off, that's the big dilemma scientists are trying to solve here.
So, how do you fix a problem like magnesium? Well, that brings us right to our next section, crafting a new alloy. This is where the researchers really put on their chef hats and get to work in a super high-tech kitchen.
All right, check out this recipe. Of course, the base is magnesium. We need that lightness. Then, for strength, they add in some aluminum and tin. But here's the secret sauce, a rare earth element called neodymium. Its job is to create these tiny, super strong support structures inside the metal, kind of like microscopic rebar. And finally, just a pinch of manganese to refine the whole mixture. You can see, this is no accident. Every single ingredient here has a very specific job to do.
But look, the recipe is only half the battle. The cooking method, how you actually process the metal, is just as important. So the researchers set up a test with 3 different methods. First, you've got the baseline, HHT, which is basically a simple long bake in the oven. For the other 2, they took that baked metal and rolled it out, almost like a baker rolling dough. One they did slowly, that's low-speed rolling, or LSR. And the other, you guessed it, they did really fast, that's high-speed rolling, or HSR.
And this sets up the perfect competition, doesn't it? We've got 3 samples, all from the same recipe, but each one cooked a different way. So it's time for the ultimate strength test to see which one really is the best. Let the games begin.
First up, the hardness test. And wow, the results are crystal clear right away. The basic bake sample, HHT, that's our starting point. Rolling it slowly, LSR, gives it a nice boost in hardness. But look at this. Rolling it fast, the HSR method, creates a material that is just way, way harder than the other 2. It's a huge win for the high-speed method right out of the gate.
Okay, so it's harder, but is it actually tougher? Well, the next test is for tensile strength, which is basically how hard you can pull on something before it snaps. And yeah, the pattern continues, but even more dramatically this time. The high-speed sample isn't just a little better, it's in a completely different league. It absolutely blows the others away.
And for the final round, we have wear resistance. Which one is the most durable over time? For this test, a lower number is better, and the results totally seal the deal. The high-speed sample has the lowest wear rate by a mile. It is a clean sweep. 3 tests, 3 decisive wins.
And you don't even have to take my word for it. The researchers summed it up perfectly themselves. They just stated plainly. The mechanical properties of the high-speed sample were higher, and the wear rate was lower. Across the board, HSR is the undisputed champion.
But this is the big question, right? We know what happened, but why? Why does rolling the metal super fast make such a massive difference? To find the answer, we have to go deep inside the metal and look at its internal structure.
So what's going on in there? Well, when you roll the metal slowly, its internal crystals, the grains, they get all stretched out. And this creates these really weak spots, kind of like if you stretched a piece of chewing gum until it got thin and fragile in the middle. These weak, stretched zones are where the material fails.
But, and this is so cool, high-speed rolling is so fast and intense that it doesn't just stretch those grains, it completely shatters them. It forces a total reset, a process called dynamic recrystallization. So instead of those long, weak crystals, the metal is reborn with this brand new structure of tiny, uniform, tightly packed grains. Think about it like this. What's stronger, a wall made of big, stretched-out pieces of putty, or a wall made of small, perfectly interlocking bricks? That's the difference we're talking about. That's the source of this incredible strength.
So what's the big picture here? What does all this really mean? Well, this isn't just some neat lab experiment. This could literally be pointing the way to how we forge the future of high-performance materials.
And let's put a number on it to really let it sink in. By changing only the cooking method, not a single thing about the recipe, these researchers got a nearly 60% increase in strength. That's not a small improvement. That is a massive, game-changing leap in performance.
So why does this matter to you and me? Well, it means we have a new way to get lighter, more fuel-efficient cars and planes. It means stronger, more durable parts for everything from satellites to engines. But maybe the biggest deal is what it proves. That when you're making advanced materials, the how, the cooking method, can be just as critical as the what, the recipe itself. And that just leaves us with this one final, exciting thought. This shows we can intelligently design not just what our materials are made of, but how they're actually put together to unlock these incredible new abilities. It really makes you wonder, doesn't it? What else could we build if all of our materials were this smart?